So the final technique in our list of separating techniques is chromatography. And chromatography is of course something you've done before in first year. At that point you probably didn't realise you were actually doing a separating technique. You probably just thought it was a cool way of making some pretty colours on a bit of paper. It is actually quite a useful technique for chemists to use for one particular purpose. If you've got a mixture of soluble substances inside a solution, it's quite hard to separate them apart. So if you've got 4 or 5 different inks dissolved in water, there's no kind of straightforward easy way to get those inks apart from each other. Chromatography pretty much is the only way you can do that. It's separating them out on basically a bit of paper from that solution. So there is a wee bit more detail in terms of what you have to be able to identify and calculate with chromatography, but I'm going to go back to your notes in a second. I'm going to just go over the key points again just on the paper here. So what chromatography is, just to remind you, it involves getting a bit of paper. Technically speaking, this is called chromatography paper, but essentially it's just filter paper cut into a rectangle. The first thing you might remember doing is putting a line across the bottom, and the line you draw across the bottom is called the origin, where everything starts from. You might remember you had to do that in pencil, because if you do this in pen, it basically falls off and goes into the solution. So a pencil line, and you only put a pencil X where you're going to put your mixture. Then you'll get your particular mixture. Now you probably used a marker pen in first year, which is a mixture of inks dissolved in a solvent, normally water. And we're going to spot that onto that X. So we want to see what different colours are contained within that spot. How we do that is we get a beaker and we put our piece of paper in the beaker. And we fill the beaker up a little bit with water. The important thing you might remember as well, it was important that you didn't fill the water up too high. It has to touch the bottom of the paper so it can soak through the paper, but it can't go above that line. If it goes above the line or above the spot will just dissolve in the water and kind of end up colouring your beaker and not going up through the paper. So then you left your chromatography paper to run, and what happened is the water gradually soaked its way through the paper up to the top, and as it did that, the ink spot moved up with it and started to separate out into the individual inks that make up that spot. So you might have got a range of different colourful little spots showing different shades of ink using that particular marker pen all the way to the top. What you normally do as well, which you might not have done at the time, you normally mark on how far the solvent or the liquid gets up, in this case water, just so you can keep track of that. So that's maybe how far the water got up to the top before I stopped the experiment. So that's the experiment you looked at in first year. It allows you to separate different ink spots out or different soluble things out. That could be dyes, could be amino acids or proteins or things like that. Now we're going to update this wee bit to make it GCSE ready. There are a few additional terms you're meant to know about that experiment in terms of how you describe it. In any chromatography experiment, there are what we call 2 different phases or 2 different parts of it. There's a stationary phase and then there's a mobile phase. The stationary phase, you think about what the word stationary means, it means doesn't move. It's the phase that kind of stays still or doesn't do anything in the experiment. In this case, the paper, the chromatography paper, is known as the stationary phase because it does not move throughout the experiment. The mobile phase, mobile means moving, the mobile phase moves during the experiment and causes things to happen. In this case, it's the liquid, the water in most cases, is known as the mobile phase. The reason we've got those kind of general terms is there actually are a few different types of chromatography. Paper chromatography is just one type, but these 2 phases are true for all types of chromatography. So stationary phase for now just means the paper, mobile phase means the liquid going through it, the water. A couple of extra terms just to highlight. We refer to that line like I mentioned at the start. This is known as the origin line, where the ink starts or where the mixture starts. And the line we draw on sometimes to show how far the solvent gets up is known as the solvent front. You could potentially be asked a little bit of explanation about why the spots move up by different amounts, which maybe is something you looked at the time you did this in first year. The reason this red spot is moved higher up than this purple spot is to do with how attracted those spots are to either the water or the paper. If you think about 2 different scenarios here. The water is going through the paper. It's going to go over the top of the spots. The ink spots have a choice here. If they're really attracted to the water, they can attach themselves to the water and end up going very high up the paper because the water is going high up the paper. Conversely, if they're very attracted to the paper and not attracted to the water, they're going to stay quite rooted down to the bottom of the page because the water's not that able to carry them up. So it's to do with how attracted they are to the water versus how attracted they are to the paper. A spot that goes very high up the page will be quite attracted to the water because the water is able to drag it very far up. However, something near this bottom of the page, bottom of the paper, will be quite attracted to the paper because the water wasn't able to pull it up that much. So it's to do with the attraction to either the paper or to the water. So most of that should hopefully be in your notes just to kind of run you through it. This describes what happens. We've talked about that. A couple of wee points here. The filter paper is known as the stationary phase. The solvent or the water is known as the mobile phase. Here's a little sentence about what I talked about in terms of why they go up by different amounts. Substances that have a stronger attraction to the solvent, the liquid, and are more soluble in it, will move quickly and travel a long way up the paper. Turning that around, substances that have a low attraction to the solvent but a high attraction to the paper will not move very fast up the paper and will stay close to the bottom. So that's the ins and outs of how chromatography works. There's one more wee consideration you have to know about one way we can measure a chromatography experiment. Because here's the scenario. If I do a chromatography experiment on a particular substance, then my friend on the other side of the world does a chromatography experiment on the same substance, we should get the same results. In other words, that particular spot for that substance should go up the paper by the same amount for both of us, because it is the same substance, and if we're using the same paper, same solvent, it all should be the same. That's quite a useful technique, because what that means is I might be able to identify an unknown substance if I'm able to compare it to other people's experiments. The way I'm able to fairly do that is by calculating for that particular spot in the experiment what's known as the RF value. The RF value gives you an indication of how far a spot has travelled up the paper. Now there's one tiny complication with that. You might think, okay, fair enough, you just measure how far the spots go up the paper. The thing to consider is, for different experiments, you might not let the experiment last as long, or you might not use the same length of paper. So the distance travelled by the spot itself isn't what we use to work out what's key about the spot. What we actually use is a ratio. We use the ratio of how far the spot has travelled up the paper compared to how far the solvent's travelled up the paper. Because that ratio should be the same in every case. Because if I don't let the solvent travel up that far, so my solvent runs very low, then my spot won't travel up that far. However, if I let the solvent travel up right to the top of the paper, my spot should travel a lot further as well. So the key thing I'm looking for is comparing the spot distance to the solvent distance. In your booklet you got a wee equation. Now the equation maybe seems a bit complicated. When we look at real examples, it seems a lot more simple to you. We use what's called the RF value. The RF value is actually a simple calculation you do in your calculator. You would take your distance moved by the compound or your spot and divide it by the distance moved by the solvent. So, just a wee calculation you do in your calculator. You normally give your answer a decimal rather than a fraction. You give it normally 2 decimal places. It's going to be much more easy if you actually look at an example. So at the top of your next page, page 9, here's a worked example. Here's what your chromatography paper might look like at the end of the experiment. This is where your experiment started, the origin. Your solvent front got up to the top here where this line is, and this is how far your spot got. My RF value compares how far my spot got to how far my solvent got. So you need to measure two distances. Distance traveled with the spot. Have to make sure I go from the origin, not the bottom of the paper, go from the origin where the experiment started, 2.1 centimetres. How far the solvent got is again taken from the same distance, the origin, to make it fair, and goes a wee bit further, it goes up to the top, 2.8 centimetres. So all I do in my calculator is 2.1 distance travelled by the spot, divided by 2.8 distance travelled by the solvent, put in my calculator, that gets me 0.75, and that is my RF value. And again, the reason why that is useful is that if my friend on the other side of the world does the same experiment with the same spot, his spot should get the same RF value. It might not go up the same distance in both cases, but the ratio should always be the same, and that gives me a way I can identify an unknown substance by looking up in a book or like a data book. So there's a little chance here at the bottom of the page for you have to go practicing calculating RF values. This is actually a question that could come up in the exam. They have got you before to measure lines and work out RF values. I'm going to do the first one for you, then it's going to give you the answers to the last three so it doesn't take too much time in the video. So what you need is just a ruler and a pen. So in this first example, it's not really a proper question, but the question would maybe say, calculate the RF values for all of these spots in this chromatography experiment. So I need two things for an RF value. I need distances for the spots. I also need distances for the solvent. I'll go for the solvent first. So I'm looking at the origin where the experiment started, looking at the solvent frontier where the experiment finished. And if I measure that line, I can tell that this solvent has travelled. I make that line up 4.8 centimetres. I therefore need to, so that's the distance travelled by the solvent, need to work out the distance travelled by the spots. Little exam tip, you're generally looking for the middle of the ink spot if it's quite big. So if I look for this top one, it's travelled, I make that 4.2 centimetres. I'll calculate in a second. My second spot travelled a little bit less, it travelled 2.1. And my lowest spot only travelled by, I make that from the middle, pretty much exactly 1 centimetre. So then I grab my calculator and just plug that in. Remember, I don't leave it as a fraction, I leave it as a decimal. So for this top spot, I do 4.2 divided by 4.8, which gives me 0.88 to do 2 decimal places. My second one, I do 2.1 divided by 4.8, which gives me 0.44 to 2 decimal places. And the final one, I do 1.0 divided by 4.8, which gives me 0.21. So that'll be how to do the calculation. So have a go yourself with your ruler and pen. Try and calculate the rest of these RF values, then I will show you the answers in a wee second. So these are the answers I got. Yours might be slightly different, hopefully in the same ballpark. So for the second one on the right hand side, 0.75, 0.56, 0.10. These ones down the bottom, 0.88 for the top one, 0.25, 0.08, 0.88, 0.67 and 0.46. So that's it for chromatography. It's a little bit more detailed than the other techniques. You know a wee bit of terminology about the phases and the solvent front and the origin, a wee explanation for how different spots travel up by different amounts. Then a way of comparing spots to each other is to calculate their RF value, which is the distance travelled by the spot divided by the distance travelled by the solvent.